Hello, good morning, everyone. My name is Emanuele Gruppioni. I'm the technical director of the research and training area at Centro Protesi Inail. And let me introduce Alberto Dellacasa Bellingegni. He's a researcher of the research area. So in this morning, we want to show you questions and issues concerning the human intelligence and learning algorithm applied to the control of upper limb prosthetics. But first of all, I would want to, you can show the presentation, please. Okay. A brief introduction of which is Centro Protesi Inail, that I suppose no one of you know this structure. That is a structure located in Budrio, in Bologna. Is a structure of the Inail, that is the Italian Insurance Against Work-Related Injuries, and is the headquarters is located in Budrio, but we have also the branch in Rome and a branch in Lamezia Terme. Also, we have assistance points to have more proximity between our patients and our service. So it's quite strange that a public insurance like Inail, I suppose some of you knows that every company in Italy pay an insurance against work-related injuries. So the particularity is that Inail is not just an insurance, but have a healthcare system that is parallel in some way to the national healthcare system, with a lot of difference, particularly concerning the treatment we have in, for our patients. Because there is difference between the, payment for the patient that have injuries in the workspace, and the patient that have no this kind of injuries, but it's outside the work. So the guarantees are quite different. So at Inail Protesi Center, Centro Protesi Inail, we deal with patients with amputation, particularly with external amputation, so without they lost pieces of his body. So our model is based on the fact that we put the patient at the center of a path, so to have all the service around the patient just in one location. So to avoid the patient go from a center to another one, to have the wheelchair, to have the prosthesis, to have the support, psychological support, and so on. So in just one structure, you have more employees that support the patient in all the aspects he need to restart his life. So to come again to the work, to come again to the society. So we have psychological support, we have the fabrication of the prosthesis, we have the support for all the life, also the license, to drive again, and so on. A lot of patients. We have more or less 10,000 of patients per year, and so a lot. Is I think the biggest structure for prosthetics in Europe, and one of the biggest in the world. And also we have a lot of activity concerning sports, because sports is for us an important public representation of the results. A patient that have a disability can reach with our aids. So going on, speaking about the research, that is one of the technical areas of Inail Prosthesis Center. We work in research plans, more or less contains a lot of projects that are long 26 months, and with short, medium term perspective, and medium, long-term perspective. So we have projects that want to gain results for the patient immediately, and projects that are based research, so with more prospective profile. So we have 5 research lines, that is rehabilitation robotics, prosthetics, upper limb prosthetics, lower limb prosthetics, evaluation systems that are more or less are concerning system for evaluation, for patient evaluation in clinical trials. We have a lot of clinical trials approved by the ethical committee and the Ministry of Health. And we have surgery and rehabilitation. We show in the presentation also some kind of application treatments that require surgical intervention to be applied. This is the network of the research. So you see a lot of institutes that work with us, in collaboration with us. So the Inail Centro Protesi is at the center of this network and coordinate all the projects with Politecnico in Milan, Istituto Ortopedico Rizzoli in Bologna, Scuola Superiore Sant'Anna di Pisa, University Campus Biomedico in Rome, and so on a lot. Obviously the CNR, that is the biggest research institute in Italy, and so on a lot, because you see there are very difficult challenges in this project. So it's not possible for us to address all the questions that are inside the project. And what we do about the research, we design and co-design the research project, and we manage and coordinate all the activity inside the project. We define the functional specification, and we extract from this functional specification this technical specification, and we do directly a part of technical development. And finally, our structure is the main structure in which we develop clinical trials, just to test our technologies. So the Centro Protesi Inail develop a lot of activities, but in a particular way that is important by the method we use to address this project, because we have the user-centered design approach. So the patient is involved in the technologies in the project starting from the beginning of the project. So we don't develop just for the technology. It's not just technology-driven project. It's a research based on the needs and the perspective of the patient. That is important thing for us, because you know, probably there is a lot of research that is technology-driven, and in our point of view, is not useful for patients. So this is a representation of the methodological work that we apply to all the projects. So we have a lot of experience. Our structure starts in 1971 with the first research activities concerning upper limb prosthetics. Is by the Professor Arne Schmidl, the first patent for myoelectrical hands. And in the workflow, we have the functional specification, as I told before, technical specification, that are the specification that come from the functional. So, for example, I want with prosthesis to bring a glass of water. Okay, this is understandable for a patient and for a technician, but the technician have to translate this simple specification in which is the velocity of the the hand, which is the force we have to apply to motors, which is the control we have. So a lot of things that is not so simple for a patient to understand. So which is this is the difference between functional and technical specification. So we're going on with design. Normally there is a feasibility study. So we use a lot of CAD system, so the design at the computer, and electronics, mechanics, and so on. And we realize these prototypes. We try this prototype inside clinical study, and we verify in this study which is the performance and if the technical specification we plan are effective. So if the validation is okay, we're going on with the other development for the fabrication, for final fabrication. If not, we start again and we redesign all, and we repeat all the process for clinical trial and validation. So just for each line of research, some example of projects. The first of these concerning rehabilitation robotics is the twin exoskeleton. Is an exoskeleton for lower limb for patients that have spinal cord injuries, so that are not able to walk. And we started in 2010 testing rework exoskeleton. That is the first one exoskeleton in the market that have 4 joints, 2 joints for the hip, 2 joints for the knees, and is able to support the patient starting from the sitting position and going to the stand position to walk by means of a sort of tilt sensors, and from walk to sitting again, and to do stairs, to do ramps, and so on. So we with this test we check that the technology is interesting, but it's not suitable for treatment because point of view was critical. So in our research project we develop a new one exoskeleton that is the twin is more or less have the same structure of the previous one, but have you know, when you have the technology you can implement all. If you buy the technology, you have to use only the technology. You can, for example, in this case, there is no possibility using rework to personalize the walking pattern. So if you develop the technology, that is our point of view for all the technology, you are able to do what you want. And for the twin, we just I want to show you the last version for the prototype. In the next month, there will be the final version that is more beautiful and it's more functional, and have a particularity in comparison with the exoskeletons that are on the market. That is a monitoring system. So a sort of sorry, suite? Yeah, thank you. Sorry for my English. And is able to monitoring the heart rate, the breath rate, and the activity on the muscular of the upper region of the body. So to understand which is the condition of the patient, because it's important that you have to imagine a patient that are in wheelchair from 10 and more years. So there is a lot of problem to use this kind of device. So we develop also all the system we need to understand which is the path in which the patient have to be, so to increase the performance with this kind of devices. Okay, just we want to show you a video. Is modular, so a patient can choose the right pelvis size, also the femoral size, also the lower limb size. You can show also at our stand in the Piazza Unità d'Italia. And here they're working. So here we have 4 motors placed in the hip and in the knees. We are working also for the wrist, because the wrist, the ankle, because the ankle is important for the generation of the path, the walking path. Okay, you can see it's needed to use crutches, sorry, and to have a caregiver that support, because it may be dangerous. Okay, but it's important because these kind of devices have an important role in the psychological aspect, because a patient gain again the upper position, and is important also because the mineral part of the skeleton is increased by this kind of gym. Okay. If you have questions, please don't hesitate. So, going on, we have evaluation system. The Rientra project is a project that is a platform to simulate a wheelchair in virtual reality, and a platform, physically platform, that increase the simulation. So we have this platform that, as you can see, rotate and so on, just to have a more immersive environment. And the question is, the aim of this project was to understand which is the cognitive load for patients that have some impairments, not only from the physical point of view, but also from the psychological point of view. And based on this experience, that is a quite advanced system, we are developing also the Riparto project, that is the same things, but for a platform that simulates driving. As you can told before, we have now a system that supports the local commission to give to patients that have an impairment the special patent. You know, there is when you have an impairment, the normal license is not enough, so you have to gain the new special patent for driving. So we want to put together the technology developed, so to have a more experience in the driving for cars. So going on, lower limb prosthetics, we are developing a knee and an ankle that are active, that push ahead the patient, because normally the prosthetics today have just a control of the velocity of the knee. So there are knees that are electronic control, that adapt itself at the rate of the walk, but are not put energy inside the walk. So it's the patient that has to push the walk. With this kind of devices, we are able to put energy inside the walk. So to support a patient that maybe are old, and to gain a more economic walk from the energetic point of view. So you can see the first trial with this kind of device. The name is Hyperleg. It is a mix of two technologies. It is electronic control, but have a motor inside and an hydraulic part that is modulated by the electronics. So normally during the walk works only the part, the hydraulic part. When the patient, for example, have to do stairs, the motor intervenes to support more the patient. So we speak about an ascend. An ascend is a polyarticulated end, so have all the movement of all fingers. Is a quite interesting design. We win the Compasso d'Oro award for this design because it's beautiful, yeah, it's important. And but have a lot of functionalities just with one motor. That's important because we have all other polyarticulated ends, but have just one motor for each finger. That may be interesting, but it's quite difficult to control, very expensive.
Hannes nasce dalla collaborazione tra l'Istituto Italiano di Tecnologia di Genova e il Centro Protesi Inail di Budrio. È una mano protesica poliarticolata a controllo mioelettrico di nuova concezione, in grado di restituire oltre il 90% delle funzionalità perdute alle persone con amputazione di arto superiore.
All'età di 16 anni ho subito un infortunio sul lavoro. Ho perso la mano destra. In questi anni ho avuto l'opportunità di utilizzare le protesi tridigitali, però non aveva quelle caratteristiche che mi riportavano a una mano naturale. Le caratteristiche principali di questa mano sono la morbidezza e la capacità di adattarsi alla forma degli oggetti che voglio afferrare. È cambiato qualcosa in me, non più dar priorità alla mano sinistra, ma una condivisione delle attività fra la mano sinistra e la mano destra, come se avessi due mani naturali. Si avvicina tantissimo a una mano naturale. Combinata al polso mobile ho la movimentazione della falange.
Okay, as you can see, it's quite realistic motion, but with just one motor. That is important thing, and with this design, it's possible to have a lot of force in the end, and to have also a particular mechanism that adapts itself to the shape of the object, but not also when the hand grasp an object, but also if the hand grasp the object. You can see in the image, and we switch off the motors. The finger are not blocked in this position, but it's possible to shake the object inside, and the finger follow my external solicitation. So this is the main feature of the harness. And so we publish in Science Robotics, that is a publisher that is important publisher in literature, and we develop a product that is certified. So just to give you an example of the path we use from the prototype to the final product. The TCCA certified, so we can use it on the patient. And we're going on with this project, just develop also the wrist and the elbow for a patient that contract an amputation that is more proximal. So which also the elbow. We are developing also the shoulder, that's important. But you have to consider that more weight. So, because we try to realize prostheses that have to be lighter. The patient have to support all the weight of the prosthetics just with the amputee reason. So it's important to have prosthetics that are light. Surgery and rehabilitation. It will be more understandable after with the presentation of my colleague, because just in briefly, if you have an amputation of the transradial amputation, okay, there are a lot of muscle that control the real hand, okay. But if you have an amputation, if you got an amputation on the humerus, there is not this situation. There are no more muscle for that, for the control of the hand. So to regain signals that are useful to are needed for the control of a complex prosthesis system, we need some intervention to regain this signal. And an opportunity is the TMR, targeted muscle reinnervation. That is a reinnervation on the certain muscles that are no more useful, with the nerves that naturally controls the hand. That's quite strange things, but it works. We will show you after some video. Obviously, it requires a surgical aspect that so is not suitable for all the patients, because you can imagine a patient that got an amputation, another intervention is not so simple. But from the functional point of view, is very interesting. So another project in this line is MyoPro. With the aim to build muscles from staminal cells. So with the 3D bioprinting is a new technology that we try to use, starting from staminal cells of the patient, and to realize muscle, because we need muscles to control prosthetics. Okay. So is the what we do with the result of the research. So as you understand, we have projects that realize the result directly on the patients. That's an important point. But also we have projects in which we are not directly with the structure involved, and so we try to produce patents that we give to companies that are interested in these technologies, and the company develop the application based on these patents, and we got a lot of industrialization activities for the application of this technology on our patient to increase the quality of their life. Directly inside the Centro Protesi Inail, because we have the production area, or to put inside other companies these technologies and to buy these technologies. Okay? So, if we have question at the end of the presentation, I'll let the...
Good morning, everybody. So far we've talked about the devices we develop. Let's now talk about how we control them, in particular how we control upper limb prosthetics. Right. For upper limb prosthetics, the state of art is represented to what is called a dual-site myoelectric control system, which relies on two electromagnetic sensors, which samples the muscular activity on two agonist-antagonist muscles, such as the flexor and the extensor of the wrist. Those two muscles can be contracted in a separate way, right? So if we flex the wrist, we notice that the bottom part of your forearm is getting contracted while the upper part remains relaxed. Contrary, if you extend the wrist, the upper part is getting contracted while the bottom part is remaining relaxed. Using sensors, we can then understand which one of the two gestures the amputee subject is performing, right? Those two signals are then linked for controlling a prosthetic device, like showed in the video before. Can we start again the video? So, all right. Well, yeah, the center one. Thank you. By the way, that is previous. Let me take care of it. Okay. Well, in the video was shown how the prosthetic hand was controlled. Leave it like that. Okay, awesome. Oh, awesome. Perfect. Now we can see the two signals. On the top part, in blue line, we see the signal for the opening of the hand, and the bottom part, the closing. Now we simulate how the hand is controlled by a user with the hand. But the amputee subject can do the same things with his forearm, right? This is a technique that is robust and reliable, right? But it's quite slow and unnatural, right? In case of multi-limb prosthetic hands, active multi-limb prosthetic hands, we cannot control all the limbs together, right? We can control only one degree of freedom, so only one active joint per time this way. So if we have a prosthetic device that has an active wrist or also an active elbow, we need to select which is the active limb, all right? How can we select the active limb? Well, we rely on a joint selection strategy, right? Which exploits a trigger signal, right, for switching between or among active joints, right? Typically, this signal is achieved by a co-contraction, which is the simultaneous contraction of both the control muscles, all right? In this way, we co-contract, we contract both the signal muscles, and we switch between active joints, right? In case we cannot perform the co-contraction, we rely on external switches, like little buttons, which the user can press with the hands or against its body. This control, as I said, is quite reliable and robust, but obviously suffer from limitation. The main of them is it's not applicable to all the kind of amputations, right? If you think about very short stumps for the elbow, the shoulder, or shoulder disarticulation, for instance, we don't have any muscle that can be used for controlling the prosthetic device. But not only. Even in cases, in the best case scenario, like the one showed before, this control is quite slow and needs a big cognitive effort from the user, right? And cannot exploit all the potential that the nowadays prosthetic hands that we can find on the market, the multi-finger prosthetic hands, we cannot exploit all its features. So for enhancing the performance and making the task simpler for all kinds of amputation, here comes our research, right? Our research aims to enhance the performance that nowadays prosthetic device we can expect from nowadays prosthetic device. And we have invasive and non-invasive techniques. Talking about the non-invasive techniques, well, one of the most promising techniques is represented by the pattern recognition. Pattern recognition is a technique that relies on artificial intelligence algorithms. We substitute the two signal muscle, the two sensor we placed in the forearm, with an array of them, or even an high density sensor, in order to map, to detect the whole contraction of the forearm, right? If we, there is the video that is not going. Okay. Well, if we contract sulla sinistra, on the bottom left, if we move our hand, we generate in the muscles a muscular pattern contraction, okay? We record the muscular activity and we are able to feed it to an algorithm which is able to detect the motion intention, right? And then we can map it in order to move our prosthetic hands. You can see my former colleague over there that is performing an algorithm that I developed years ago, which is called the nonlinear logistic regression. Well, I developed the code. It's not my idea. It's a pretty old algorithm. I just ported it into a microcontroller, and as you can see, is moving the hand. You know, is mapping the hand is mimicking what my colleague is performing. Right. Okay. There's a bunch of math behind it. We also developed combined index, neural index for evaluating the performance of the algorithm. And thanks to those, we were able to exploit the same algorithm not only for the hand district, but for controlling an entire prosthetic device. On the right, we can see that controlling that device is an amputee user. The blue band wrapped around his forearm is mapping continuously the muscular activity, right? And the left hand is just only used for showing us what he's trying to perform with the hand we cannot see. Thanks. Yes. Sorry, I forgot to tell that the amputee subject is able to control the device because in 70% of cases after an amputation, there is the chance of developing what is called the phantom limb sensation. So it's a phenomena with which the user still feels the arm, even if the arm is no longer present. And not only he feels it, but he's also able to control it, to move it. Controlling the phantom limb generates into the residual muscles contractions that are extremely similar to the one we would have with the arm present. And thanks to that, the same algorithm can be exploited for controlling a prosthetic device. All right? Thanks to those advancements, at the moment we are designing through our projects new advanced in technology prosthetic devices, actually extremely advanced. We decided to develop a new prosthetic device with all the sensors, all the functionalities in order to test, develop, and exploit, push to the limit those kind of algorithms. So an IP-sensorized prosthetic hand, which we hope could revolutionize the prosthetic field. The main problem of the previous technology is that it's very hard to control more than one joint per time, right? It's hard to control in a robust way simultaneous limb movement, because robustness of the control is very important for prosthetic devices. Imagine you are holding a glass. It's very important that the glass is not released against our will. You know, because you are moving the hand, the sensor can detect some noise, there are other phenomena, like the sweat and stuff like that. It's very easy, those algorithms are sensible to this kind of problem, and it's important that the algorithm is robust. So, plus, if we have a very short stump, or a shoulder disarticulation, or the muscle are extremely damaged, and we cannot use them, it's impossible for the user to control the prosthetic device. How can we intervene in these cases? Well, there is a solution which is based on a surgery. The problem can be assessed surgically, so in an invasive way, right? And we are talking about the targeted muscular reinnervation. This is a technique, a surgical technique by which a spare muscle of an amputee is denervated and then reinnervated with the residual nerves of the amputated limb, allowing a spaced division of the muscular signal used to control the different joints of the prosthetic hand. As shown in the picture, then nerves that were destined to irrigate a muscle that is no longer present, right, is taken, denervated, and then attached, physically attached, reinnervated on a spare muscle, a muscle that is no longer needed, such as the chest muscle, right, the breast. That the same muscle, a big muscle, serves as a biological amplifier of the signal. So when the user thinks to move the hand, what generates a contraction in the chest, right? We put the same electromyographic sensors on the chest, not anymore in the forearm, but on the chest. The chest muscle is then splitted into part, and in this way we surgically created independent control sites, right? We can put electromyographic sensor on this site and perform simultaneous control of prosthetic limbs. We, Inail, took part now at the third project in which actually we relied on this technique. This is a girl that is shoulders is articulated, and she received the treatment, the TMR treatment. We performed 5 active site muscles. Obviously, is a surgically procedure, so requires long time before it's actually used in a reliable way. 8 months for the reinnervation, because the nerve has to grow on the muscle, has to be attached before being able to send the signal to the muscle and the muscle to contract. And then we waited 12 months before the trial. But in the end, we can see, again, she is performing the task with the hand we can see, and then controlling the same one with the residual muscle. On the chest, we can see the electromyographic sensor that is detecting the muscular contraction, because she's thinking of controlling the hand or the arm, and the chest is contracting. Right, it's quite magical, but it works. Not only, we observed another phenomena that is discussed in literature, which basically the same subject develops like a brain link between the area that is now reinnervated with new nerves. So when you touch from the outside the area, she feels like you are touching her hand, right? And is called sensory reinnervation, you know, because now you're not developing a control signal, you are developing a sensory feedback kind. And we tested it using both tense and vibratactile systems, right? This is another technique. When there are amputation, like the previous case, or short stumps, it's very hard to get to create a socket that is able to support the weight of the prosthetic device. A solution in this case, which involves also surgery, is the osseointegration. Right? In this treatment, which involves true surgical procedure, firstly, a titanium fixture is surgically attached to the skeleton, like a dental implant. You know, like when you go to the dentist to substitute one of your teeth. It's just bigger. And second, procedure 6 months later, which involves a skin-penetrating abutment to which the prosthetic device is attached. It's basically just enlonging the bone, right? And the prosthetic device is no longer a tool, is becoming really a part of your body. That subject received as well the TMR treatment, but not to the chest, but to the bicep and the tricep, on the bicep and tricep muscle. Those muscles are no longer usable because the subject doesn't have the elbow. So those muscles are destined to shrink, to get eliminated by your body. But if we use them for target muscle reinnervation, we can achieve performance that outlies completely the traditional control, the myoelectric control I showed before. This is, look, osseointegration, no socket, nothing, just and is able to perform. Is actively controlling the elbow, you know, for performing, that is something it's impossible to perform with the traditional control techniques. And we are very happy about the result in this case. This subject also received what I told you before, the targeted sensory renovation. So not only the muscles, but also the same nerves are attached to a more superficial layer of the skin. I'm using simplification, by the way. I'm making it more simple. It's to upper layers, to more superficial layers of the skin, in order to develop, to investigate more in depth these kind of phenomena, the sensory renovation. Moving more into invasiveness, we also tried in the last years a project. We took part of a project which involved neural interfaces. So far we talked about muscular interfaces. Now we try to move into sci-fi, let's say, and to interface with the nerves. There are two main types of electrodes. One is the time intraneural electrodes, which is showed in the video on the left, and the cuff electrode. Why this? Because the main draw side of these kind of surgery, or these techniques, is represented by the reject phenomena, right? The intraneural electrodes introduce a foreign body reaction, FBR, that results in tissue encapsulation of the device, causing progressive decline of the electrofunctionality, because it's dropping the electrode with isolant material. So it's no longer conducing electrical stimulus, so it's pretty much unuseful. And sadly that happens after pretty much a pretty short time, such as 3 months or 12 months in the best case scenario, for the intraneural electrode. The cuff electrode have a longer life, right? So we decided to take to take these two electrodes and apply them to a subject into the two nerves of his forearm, in order to restore the sensory feedback, right? Is not used at the moment for controlling the prosthetic device, but for giving back the touching sensation, right? We send through those nerves, through our interface, exporting our electrodes, electrical stimulus, in order to simulate the same pattern that the body would have in normal conditions. And we were able to restore part of the sensation of the hands, as showed in the bottom part picture, and to send information regarding the slippage of objects or the force applied on objects through a prosthetic device. In this video, we can see the subject performing some tests, experimenting, and we observed an increase of performance in controlling these kind of devices when sensory feedback is provided to her, in respect only to when she was relying only on her sight, on seeing what she was performing. In this case, we can see quite complicated task. She's folding a little napkin, unfolding and folding. She was doing both of them. Is an experiment took part a few years ago, 3 years ago, and the same system, which exploit both pattern recognition and a neural interface, obtained a good result, very good result, which are worth a publication on Science in Robotics again, which is a very famous journal, prestigious journal for this kind of research field. After 6 months, the subject got into another surgery for removing the implant, because it was time to remove the neural interface, but she maintained the control of the prosthetic device, exploiting pattern recognition algorithm. And that's it. That's basically the latest advancement in the upper limb prosthetics that we are performing at Prosthetic Center in Budrio. if you have any question, please, we are here to answer to your questions. Thank you very much.
Just let me point an important thing. All these algorithms of this surgery have an implication of also on the rehabilitation path, because as you see before, and there is in the past phantom limb was removed from the
Yeah.
physiotherapist, because it's not useful, and maybe maybe in the real life of the patient is not a good thing. In this way, we need phantom limb to control prosthesis. Also, if you control a hand with extension and flexion, it's different that if you control a prosthetic thinking about your lost hand. It's completely different. So also the rehabilitation path is completely different.
Yeah, is affected.
And also, we need we obtain a best embodiment of the prosthesis with this technique, because you have the impression of that the prosthesis is inside, is a part of your body.
Yeah,
Okay.
correct. I forgot to tell that. Yeah, thank you. Yes, it's indeed a change of paradigm, because you are controlling your hand. You exploiting something that since 10 years ago was seen as a bad thing. It's kind of revolutionary. It's the new way of controlling prosthetic. It's the future of prosthetic device, in my opinion. That's an opinion. And that's it. And changes also, well, changes, it might change the way in which those subjects are rehabilitated, are taught, right? If we take a subject, and since the very beginning of the rehabilitation process, we teach him, we tell him, train your phantom limb, maintain the movement, better the movement, better the signal. Better the signal, better the classification and the control, and so on. Or that's it.
Okay, thank you. If you have a question?
There is a question.
Thank you for the presentation. Thank you so much. And my question is, who is eligible to get this kind of prosthetic limb? Is there someone who has health problems, who is not able to get one, elderly, or what's the age for it?
Okay. The age, there is no real answer to that. There is no real problem to the age, or that can. We are talking about, well, wait a second. We are talking about the surgical implants or the pattern recognition. The surgical implant, yeah, in this case is better suited to younger people, because there is a surgery involved, right? So the bone has to be a good bone, you know, for receiving an implant and stuff like that. For the target muscle reinnervation, again, bigger the muscle, better is the signal, and so on.
So the problem is the risk for the patient.
Yeah.
So it's better for a young.
Yeah, young subjects are better suited for receiving surgery. Indeed, surgery is at the moment the only backside of this technique. But you know, it's very experimental. It has been done. It's working, but it's still experimental, because there are ethical questions to be addressed. It can be used only in certain cases, and for research purposes at the moment, I think, in Italy at least.
Thank you so much for the presentation. My question would be, what is maybe the most common challenge you faced in your day-to-day work while developing these techniques? Thank you.
Day-to-day.
So probably the first one is to grow the information we need to control a more realistic prosthetics, and the feedback. So we have to close the loop bidirectional communication between the body and the prosthetics. This is the first question. So there is another one that is maybe strange, but from the technological point of view, we are, I think, at the top of these possibilities on the technology we have today. So the motors are very small, and the patient needs more force for the hand. Okay, it's not possible. It's very there is not so much margin of increase in this kind of things, because you have to consider prosthetic hand have a force of more or less 15 kilograms. A human hand have 40, 50 kilograms, a lot. And the patient wants a hand that is light, but is extremely perform. It's not possible today for technology problems.
At the same level, I face the control problem. How can I give him more ways to control the prosthetic device in a more robust way? The robustness is the main problem at the moment. These techniques needs to be robust for safety purposes, for thinking that it's not a device, it's a part of your body. A part of your body never fails you. Or you know how disappointed you are when your knees fails. That has not to happen, especially if it's a device that should work as a part of your body. We work in order to make prosthetic device part of the body. All right, you have to feel it as part of your body. Our goal, obviously, is creating, ideally, a real arm. That is our goal, and it's a very high standard.
This is the reason because we are going inside. Outside, the information are not enough. So inside, there are information, but we don't know the human protocol of the nurse, which is the protocol. We know the protocol for the internet because we created this protocol, but from the body we don't. Also the interface are, you see, very small, but not so small to interface really the single nerves or the peripheral system or the central system and so on.
Hi, thank you. It was a very interesting presentation. I wanted to ask, I don't know if I understood correctly, but because of the artificial, like it's in the title, artificial intelligence, like do you use it only like for the pattern recognition, and is it like for only kind of learning about the movements, or also like the electrical signals, and like do you use it, the machine learning, all this stuff? Are you using it?
We used for both, also for the neural interface. During the same experiment I showed you in the last slides, we also try to decode the human intention through the neural interface, with good result, but not as good as using the muscular pattern recognition, just because the signal are bigger. Just the muscle works as a biological amplifier again, and less noise, all less interference. The neural signal is subject to a lot of interference. Just for telling you, once while performing the experiment, we noticed that we were receiving big interference at a certain part of the day. In the morning, we were having big noise on the signal, so we were not understanding what was for. While was the RMI machine of the same hospital we were working in, and was something like 500 meters away underground, but nevertheless we were measuring the same noise on the signal. You know, it's very hard to detect completely the neural signal, but we tried and something worked, obviously, but not as well as the muscular pattern recognition. Obviously, the neural interface is a frontier challenge. We are moving to that direction, but with the nowadays technology, we reach the roof at the moment. We will try to work harder on that, but at the moment it's what we achieved.
Hello. Thanks for the presentation. I have questions, maybe two parts of the question. I see you two sitting here, but I imagine that the teams that are working behind this innovation and prototypes are quite big guys. You have engineering problems and you have software problems. So the first question, how is big the team and how different competencies you need on this kind of the project? And the second one is to have like IP protection on all your innovations, and you planning to go to the market soon, or what is the level at the moment? Is it just prototyping, or are you planning to enter the market soon? What is the situation on this matter?
So in our team there is a lot of different figures that are mainly engineers, and but you have not to imagine that are all by engineers. No, for the mechanics we need mechanical engineer. For the electronics we need electronic engineers. For algorithm by engineers normally, and informatics and so on. But also the also we have physiotherapists, the CPO, the certified prosthetist and orthotist, because it's a real complex systems, and we need all these figures to address the project. And
we rely also on our research network with other partners, which might have doctors, surgeon, and other figures, which we might lack, but in the research network we can compensate it quite well.
This is the reason of the network. So I think more or less we have more than 1,000 researchers in all the network. Yeah. And for the technology transfer, we try to put the reliable things inside the products. So ANES is a certificate, but we have ALNES, the second version with more degree of freedom, with the sensor of the fingers, and we increase the technology we transfer step by step. So because in our opinion, a patient have to, in our opinion, obviously, a patient have to use these things in the real life. So you see all the video that work inside the laboratory, but it's not the same to use this technology at home. So it's a long way. And so we have various level of TRL project. So we start from the basic research. Yeah.
Thanks again for the presentation. I wanted to know if these prosthetics or these projects can also be used by someone who has been born without a limb, not that like he has never had an arm or a leg.
Well, pattern recognition, for instance, it cannot be used for people that are born with this kind of handicaps. Because they don't have a phantom limb sensation, and what they are moving is actually their body. They can use it, obviously, but it would be like learning how to drive a car. You need to perform certain things with your hand that are mapped for performing on the prosthetic device, and that is very unlikely to happen. Also because it's getting refused. They already have their hand. You know what I mean? It's different. If you lose something, you feel the need of it. If you don't, if you ever had it, it's not the same thing. You might feel the need of it, but it's not the same as losing it.
Yeah, it's possible to use traditional control prosthesis. Yeah, but right. Normally, the patient don't need aids.
Depends on the patient. If you want, you can try it. It's not. No, you cannot have it. You can. It depends if you want it. Wait for the microphone.
You mentioned ethical issue before. Which is the main one you have faced?
An issue?
Ethical issue.
Ethical issue? Well, you know, you are performing a surgery that is not needed in theory.
Practical.
Yeah, that's it. So if something happens, how can you justify the surgery? If the benefits, the results, the performance of the prosthetic device are good enough for justifying the surgery, yes, then indeed it's something you can perform, right? But that is something on an ethical level, you know, because we think everything works fine. But if something doesn't work, or simply the system doesn't work, imagine the system doesn't work. Why have I done the surgery? Why have I risked? Okay, it's a risk. It's an ethical problem.
And what about the 3D bioprinting? So how do you apply it?
Yeah, 3D bioprinting is just a support today to put inside hydrogel, you know, like, I don't know the name, okay, in the eyes, the cells that have to be survive. So this is the first point. So it's a new technology. So we are trying to put the staminal cells with some factors that determine the growth of this cell and the specialization of this cell in muscle cells and the organization of these cells in muscle fibers is really a really strong challenge for this. So the printer is one of the way to realize 3D structures, because the muscle obviously is a 3D structure, and we are able to do layers of cells, but we need a method to realize not just layer, but a 3D structure. So maybe you roll the single layer and you have a rolling system that is quite difficult because the thickness of this layer are really small, or use 3D printers. So we have tried to understand which is the best way. But well, just at the start of this field of research.
Yes, hello, thank you for your presentation. I was wondering about what is the access to people to your patients who had an accident to your technology? Is it covered by some form of insurance, or what are the costs that the patients have to pay for rehabilitation?
So our structure is open at the work-related injuries, is for work-related issues, but not only to this, also from healthcare system, national healthcare system. We are more or less 80% of patients that got an incident of the work, and 20% not. And there is a different treatment from the point of view of technology we can leave to the patient, because patients that are from Inail are covered from all the point of view, and from prosthetics pay nothing. Okay, it's the insurance that pay for it. And for the healthcare system, there is a sort of
there is a spreadsheet that lists all the how much you can be refunded from the expense you sustain for a prosthetic device, but is outdated at the moment. Is dated 19.
Yeah, 1991.
96.
1999.
99.
Yeah, and is the difference have to pay by yourself.
Yeah,
okay.
Inail indeed is an insurance. Is an insurance company that covers only the work-related accident, the work-related injuries, but offers services also to other people, as the director said.
Any other questions?
Hi, thank you for the presentation. I have a question about the implants. So, because obviously those are implanted in the body, there is a possibility of rejection. Do you encounter those or no? And if rejection does happen, what is the next step in treating these patients?
You're talking about the osseointegration, yeah.
No. No, about osseointegration, there is not a problem of rejection of the implants because we use titanium, 5 grade, and so is a material that is quite used in this kind, also in internal prosthetic. So is the same from this point of view. And we have some problem for infection because there is a hole between inside and outside. So this is a way for infection. But at the moment, also from this point of view, we got no problems with our patients, just little problem of infection that are treated with cutaneous creams.
Yeah, the infection in the skin penetrating abutment, because you have this piece of metal that actually is getting out of your skin, and around the metal, obviously, there is no skin. It's you can get an infection in there, yeah. But if you clean it, you treat like normal.
At the moment, but
normal
we know
skin
it
infection
can happen. So in all our projects about this, there's an assurance, a specific assurance, because it may happen that a patient got an infection that is maybe you have to extract the implant. It can happen, yeah. We don't know, so we go slowly by with these experimentations.
Hi, thank you. I want to ask about the lifespan of the implants. How long does it work, and will it disintegrate with the time because it's a mechanical device? Thank you.
Normally, the market is build implants that are 10 and more years for the duration. But we know the implant is not simple to remove, so stay there until it breaks. So that is the real. Okay, no one substitutes components inside of the body until the component breaks. This is the reality. But you have to declare the life cycle. That is more or less, it depends by the device. If we treat also the finger, the femoral, and so on. It depends, but 10 years.
Anyone else? No?
Okay.
Okay.
Thank you very much.
Very much.
Time is perfect. Awesome.